Hello, this is the video for 1.5. We are going to be looking at graphing techniques and transformations. So in section 1.4, the last section that we covered, we looked at the library of functions, meaning what does the square root function looks like, the quadratic, the cubed root, the cubic, the absolute value, all those functions that I'm hoping when you look at an equation of a function, you can kind of picture what it's going to look like based off of what you know that parent function looks like. Okay, those are all listed right here, those ones that we were looking at last time. Again, hopefully being able to visualize and graph any of the functions with what we learned today. How can we take those parent functions that we looked at before and change them a little bit, move them around the graph, stretch them, shrink them, that type of thing. And so here, let's first talk about, so if we take any of these functions, how you can shift them vertically and horizontally and what that looks like in your equation. So first of all, I'm going to be using in this section, I stole some of my daughter's Play-Doh to kind of just visualize what's happening. So let's say this is a parent graph. Let's just call this a quadratic, even though, yeah, I know it doesn't look like a parabola. If I take this and I vertically shift it, so I move it up or down, think about what's happening. That's a change of the y-axis. It's just moving up or down. Notice what's not happening is the shape of my graph is not changing, just the location of where it's at is changing. So that's important. Like if you're graphing a parabola, okay, it's going to look like the exact same parabola that our parent function did, except for it's going to be in a different location. Same with shifting left and right. You're not changing the shape of your parabola, you're just changing where it's located. So let's look right here. So this is really important. I'm gonna like highlight or box this because this is how in an equation that you will shift a graph, no matter what graph it is. Okay, so if we want to shift vertically, okay, what you're gonna do, whatever your function might be, okay, so that's what f of x is, whatever your parent function might be, if you want to shift it up or down, all you have to do is add a number on the outside of the function. Okay, you'll see what I mean in some of the examples, but if you add a number, it shifts it up. If you subtract a number, it shifts it down. Okay, so pretty straightforward in that case, that adding shifts you up, subtracting shifts you down. You might be like, yeah, Haley, I know that's pretty obvious. Up is adding and down is subtracting. But the reason I'm emphasizing that is because it's actually opposite when you're shifting left and right horizontally. Okay, so here now, notice the location of where you were adding or subtracting the h. H is how much you're going to be shifting. Notice now it's not on the outside of the function like the k was, but the h is now on the inside, meaning it is directly affecting the x. And think about horizontal is along the x-axis, so that makes sense. Okay, that h or k needs to be on the inside. Okay, here's where I say where it's a little bit opposite on the inside, where actually when you subtract h, it shifts you to the right. So you might think initially left and right, subtracting means to go left, but in transformations, it actually shifts you to the right. And then similarly, if you are adding, it shifts you left. So a little bit opposite on the inside. Not a little bit opposite, completely opposite than you might assume. But that's actually going to happen with any horizontal transformation. Okay, this is an example of 4 different transformations. A shift up is a transformation, a shift down, a shift left, a shift right. Those are all called transformations. So let's see what it looks like. Okay, so this is just an example of those horizontal or vertical shifts. Okay, so let's say here I'm starting with this. This is my quadratic. I know it's a parabola. Go back to 1.4, your library of functions, if you need to see what that looks like. We're going to use that to obtain this graph. Okay, so what I always like to do first is identify the transformations that have occurred. So notice it went from x squared to x squared plus 3. So that plus 3 is on the outside of the x squared. If it were in the inside, it would be inside parentheses, also being squared. And so that's an example of up. This is a shift up 3. Okay, notice it asks us to graph both of them. So I'm going to start real quick by graphing my parent function. Okay, think about 0 squared is 0, 1 squared is 1, 2 squared is 4, and even if you plug in the negatives, it will also be reflective like that. I could do 3 squared is 9. I have enough room on my graph for that. Okay, so that right there, I'm going to graph it in black, and I'm going to label it F. Okay, because that's function F, the parent function. This next one I graph is going to be G. So recognize what's happening. If all that happens is I'm shifting up 3, that means instead of starting at 0, 0, I'm starting at 0, 3. And then that same pattern is going to hold true. Over 1, up 1, over 2, up 4, 4. And then reflected on the other side as well. So every single point, if you just count where it is on F compared to where it is on G, the only difference is that it's added 3 to the Y value. Like to every ordered pair, I'm just going to pick an example like this ordered pair on my parent function is 2, 4. Notice where the corresponding point is now. Now it's at 2, 7. Okay, so when you shift vertically, the X does not change, only the Y value does. And specifically, you're adding 3 to it. Okay, domain and range for each of them. So just in general, if you are only shifting, if you're only changing vertically, your domain does not change from one graph to the other, right? Because you know the domain is the X values, the left and the right. And so in this case, the domain of my original is going to be the same as the domain of my transformation. So I'm going to label one of them f of x and one of them g of x. Okay, my original domain, notice I'm going left and right forever, so negative to positive infinity, and that's the same with my transformed function as well, g. Okay, but now the range is not the same. Okay, look at your original graph, the black one, f. It starts down at 0 and then goes up forever. But our range for the graph of G, now it doesn't start at 0, it starts at 3 and goes up forever. Okay, and so again, recognizing that if I am changing a Y value up and down, that changes the range because range represents all our Y values. Okay, so now let's look at an example of transforming. So here's the function I'm starting with, just the square root of x. And this is what I am going to graph, the transformation of it. And so let's think about here, the square root function, I'm going to graph that one first. So our domain, actually, let me just write that down because it helps me graph it. My domain for f of x, I cannot plug in any negative number. So 0 is the smallest number I can plug in. And then I can plug in any number bigger than that. Okay, so I'm going to start at 0, 0. The square root of 1 is 1. Now I'm not going to plug in 2 or 3 because I can't take the square root of those and get a nice number. So my next one, the square root of 4 is 2. The square root of 9 is 3. So that's my graph of f. I see that my domain is from 0 to infinity, and my range is also from 0 to infinity. Okay, so let's think about when we're graphing G, where is that -2 located? Okay, specifically, it is connected directly to the x, so it says x -2. It is not. Let me show you the other option. If it were this, that would be something different. Because that -2 is also underneath the square root, that means it's directly connected to the x. It affects movement left and right. And in this case, because it is on the inside, it's opposite. So to name the transformation that's happening, this is a shift right 2. Okay, it's showing exactly like what, whoa, stay co-host. That was weird. Uh-oh, please don't have you erased everything? Uh-oh. That's okay. I'll just start where I ended up. Darn it. Okay, that's okay. We're right here. This was our shift right 2. Okay, let me add my parent function back there real quick. I have that pattern memorized. Okay, so now since this is a right 2, nothing is changing up and down. So I know because of that, the domain, sorry, let me rewrite that real quick, and my range. Since I know from graphing F to G, the only thing that's happening is a left and right motion, that my range is going to stay the same. Okay, if I'm not changing anything with my y values, the range doesn't change. But my domain now, I know that every single point is going to be shifted right to. So instead of starting at 0, 0, I'll start at 2, 0. And then it's going to be the same pattern of what that parent function was. 1, 1, because the square root of 1 is 1. The square root of 4, so from my new starting point over 4, up 2, over 9, up 3. Okay, and that's my graph of G, and the graph of F was in black. Okay, so again, now recognize, like if I pick out any ordered pair and it's transformed ordered pair, notice that that ordered pair, if I write out what the point is, it's the ordered pair 4, 2. And if I write out what that one is, it's 6, 2. So again, if all you've done is shifted every point right to, that only changes the X value, not the Y value. So you can see what that transformation is. Okay, so then our range, we said it didn't change, but now our domain, it has changed. The smallest number you can plug in is 2, and then I can plug in anything bigger than that. Okay, picture what happens in the equation. If you plug in 2, you get the square root of 2 minus 2, which is the square root of 0. So that's why picture if you plugged in anything less than that, like if you plugged in 1, 1 minus 2 would result in the square root of a negative number. So that's why 2 is the smallest, and then anything bigger. Okay, so that's shifting left, right, up, down. Let's talk about now compressing and stretching. Okay, so just like there was with shifting, there's such thing as vertical stretching and vertical compressing, and then also horizontal stretching and compressing. So I'm going to make a comparison. Notice with vertical, that A value, A is the factor that you are either stretching or compressing by, what you're multiplying by. Okay, vertical occurs on the outside of the function. Okay, it affects the Y values. Vertical is up and down, affects the Y values. But here for the stretching, stretching occurs on the inside. Okay, the inside of your function. That's why A is on the inside of the parentheses. And just like, and I'll get to it in a second, but just like with shifting left and right, vertical, horizontal stretching and shrinking is opposite than what you would think. Okay, so let me show you examples. Now I think the Play-Doh is going to come into handy here. So in this case, stretching and shrinking actually does not change the location where your graph starts. It directly affects the shape of your graph, if it is more narrow or if it is wider. And so let's say this is just a parabola. How about, okay, and I'm going to vertically stretch. So it stretches if A is greater than 1. And that makes sense, right? Like if you multiply by 2 or 3 or 4, it's going to get bigger. It's going to stretch it. Okay, vertically stretching. If I take this Play-Doh and vertically stretch it, it's going to make my graph taller and more narrow. It is directly affecting the Y values. It is multiplying your Y values by some value. So instead of like 1, 1, it would be 1, 4 if I were stretching it by 4. Okay, so a vertical stretch makes your graph more narrow. Wow, let's picture, okay, let's say I'm starting with this parabola right here, and I vertically compress it. Notice it's going to get shorter and it's going to get wider. So stretching vertically makes it more narrow, while compressing it makes it wider. Okay, on the other hand, let's talk about horizontal stretching. So now look at this. This one is saying now, if your A value is between 0 and 1, aka if it's a fraction like 1/2 or 1/4, okay, if it's on the inside, it's actually going to stretch it. It's going to make it bigger. Okay, when previously stretching was if it was greater than 1, but inside the parentheses is opposite. So because of that, let's look at a horizontal stretch. So let's say we have an A value of 1/2, whatever it might be. Okay, horizontal stretch now, making it horizontally, so left and right, stretching it makes it wider. So stretching it makes it wider horizontally, but horizontally compressing it. So let's say I'm starting with this. If I horizontally compress it, it's going to get taller. It's going to get more narrow. So first, what's important is to recognize, okay, first, is it vertical or is it horizontal? Is it outside the function or inside the function? And then by what, okay? How is it changing it? Again, recognize that it's multiplying, okay? It's multiplying this time. So not adding and subtracting, but multiplying. So let's start here. We're just graphing all three of these. I didn't want to do it on the same graph because I feel like that would get a little messy. So graphing our parent function for the cubed root. Again, go back to 1.4, your library if you need. But here's what your cubed root looks like. 8, 2. And then remember, we can plug in the negatives with cubed roots. 6, 7, 8, 2. Because a negative times a negative is still negative. So there's your parent function. Now let's graph G, okay? G has a 2 outside of that cubed root. So because it's on the outside, that means it is vertical. I'll just use a V for vertical. So I know something is changing up and down, but that 2 now, we just have to think about, okay, multiplying it by 2. Oh yeah, that means it's going to get bigger. It's going to be taller. It's going to stretch it. Okay, this is an example of A being greater than 1. So now all that means that's happening. Again, I'm not shifting it. I'm not changing where I'm starting. I'm still just starting at 0, 0. But every one of my ordered pairs, okay, if I write out like this is 1, 1, and this is 8, 2, vertical is a Y value. So all that means that's happening are these Y values will be multiplied by 2. So now I know I'm still just starting at 0, 0 because 0 times 2 is still 0. Okay, but instead of 1, 1, it's going to be 1, 2. Instead of 8, 2, I'm doubling that Y value. I'm multiplying it by 2 because this tells me to. 2 times 2 is 4, so it's going to be 8, 4. 1, 2, 3, 4. So recognize vertically stretching it makes it taller, specifically by a factor of 2. Okay, over here, instead of -1, -1, it's going to be -1, -2. It's going to be -8, -4. So it is just growing technically twice as quickly as that parent function did. And that's what the vertical stretch of 2 does. Again, if you want to write out those ordered pairs so you can see what's happening, 8, 4, is it's directly affecting your Y values. Not adding and subtracting though, multiplying. Okay, so then let's look at if I move that 2 to the inside. Okay, if I move it to the inside, it is directly connected to the X, which means it is directly affecting the left and the right, which makes it horizontal. Okay, but inside is opposite. You might think that the 2 would horizontally make it bigger, but the 2 is actually going to make it smaller. This is an example right here. If A is greater than 1, it's a horizontal compression. Okay, so I'm going to call it horizontal compress here. So this one is kind of interesting. It's going to end up looking very similar to our vertical stretch. What we have to do, so picture these points that I highlighted. Okay, all that's happening here is that I am going to horizontally left and right, so the X values need to be cut in half. Okay, instead of multiplying by 2, maybe let's make note if you need to write that down. So this is going to cut X values in half because it's not multiplying by 2, it's opposite, it's cutting it in half. So that means instead of the ordered pair I'm referencing here, my parent function, instead of 1, 1, I have to take my X value and cut it in half. So it's going to be 1/2 1. So from 0, 0, 1/2 1. Instead of 8, 2, that X value I have to cut in half. It's going to be 4, 2. 4, 2. And so it's actually going to, a horizontal compression is going to make your graph taller as well, okay? It's horizontally not taking as much for it to get as tall. Okay, and so then -1/2, -1, and -4, -2. So both the vertical stretch and the horizontal compression make your graph grow quicker. Okay, with the horizontal compression, it takes half the amount of x values to get the y values that the parent function did. So I think writing out those ordered pairs really helps clarify when you're comparing it to the parent function of what's happening. So horizontal affects the x's, vertical affects your y's. Okay, so let's just practice a little bit of that, like putting it in combination, because these ones were super basic, I would say, because there's only one transformation. So let's talk about what this is going to look like now. Okay, so we're going to graph this based off of what we know the parent function looks like, the absolute value. Remember, it looks like a V. It starts here at 0, 0. And so let's graph the transformation of that. So first, when we think about the absolute value of x, let's just pick out 3 points. I know that vertex is at 0, 0. And then if I plug in 1, the absolute value of 1 is 1. If I plug in -1, the absolute value of -1 is 1 also. And again, that's just the parent function. Let me graph that so I can graph our transformed one as well. That side is a little, let me fix this one. Okay. So there's our original, the parent function. Now, before I graph it, let's talk about what each of these transformations are doing, because now there's 3 of them and they each are going to do something different. So here, let's talk about the 2. Okay, the 2 is a vertical stretch. That vertical stretch means that we will multiply y values by 2. That's what the vertical stretch means. It's going to grow the y values by 2. Okay, this x plus 3, it's on the inside, so it's left and right. But which one? It's opposite. Adding actually shifts you left 3. So what that means is your x values, you will have to subtract 3 to them in order to move them left. Okay, and then the last one right here, that is a minus on the outside, so it's a down. It's either up or down, and since it's minus, it's down, so down 5. So that what that means is our y values, we will have to subtract 5 from them. But the thing is I'm going to do this in order. Okay, I'm first going to multiply the y by 2, and then I will subtract the 5 as well, okay, because recognize 2 things are happening to the y values, only 1 thing happens to the x. So let's pick out the ordered pairs. Maybe let's talk about the x's first, because those are a little bit easier. Okay, so here are my x values right here. And it looks like all I have to do with my x values is subtract 3 to each of them, because that will shift it left, right? And so here I'm going to start with 0, will be at -3. If I take 1 and subtract 3, now it's at -2. If I take -1 and subtract 3, now it's at -4. Okay, since that was the only horizontal transformation, that's the only thing that had to happen to the x. But now the y values. Okay, let's look at our y values. Right here, the first thing I will do to my y values is multiply it by 2, and then whatever I get, I will subtract 5 from it. Okay, so let's start with this 0 point. If I take 0 and multiply it by 2, I get 2, or sorry, I get 0. If I take 0 and multiply it by 2, I get 0, and then when I subtract 5, -5. Okay, now let's start with our 1 right here. If I take 1 and multiply it by 2, I get 2. And then when I subtract 5, 2 minus 5 is -3. Okay, now let's take the y value of 1. If I take 1 and multiply it by 2, I get 2. 2 minus 5 is -3. Okay, so this is being able to graph transformations by looking at the equation. I'll talk about how to do it without these ordered pairs as well. It's just on the homework, I know you're going to be asked to fill in a table like this, so I wanted to give you an example of what that looks like. So what I'm going to do now, I'm going to go to my graph and plot these new 3 points. Okay, so my vertex now instead of 0, 0 is -3, -5. And then I'm at -4, -3, and also -2, -3. -4, -3, -2, -3. And there's our new graph. Okay, so from those points, you could identify what those were, but let's also talk about how I could do it without writing out the ordered pairs. So understanding that the vertex of the parent function is at 0, 0. The first and most important thing after transformations is to figure out where your vertex will be. So remember that stretching does not change the location of your graph. Okay, it just changes the shape of it. And so to find the new vertex, all I have to figure out is the shifting left, right, up, down to tell me where my new vertex is. So when I see left 3, down 5, where's your vertex now? Instead of at 0, 0, it's at -3, -5, right? So I could place my vertex there just based off of these two transformations. Okay, and then from there, what does the graph look like? Look at the pattern of the parent function. Usually it's just over 1, up 1, right? But that 2 is a vertical stretch. And so what's happening from our vertex now, not over 1, up 1, it's over 1, up 2. So again, if you can just recognize and understand the parent function and that pattern, how your transformations affect that pattern is going to make it easy. Okay, shifting left, right, up, down, and identifying where that means you're starting on your graph is really important, really helpful. Okay, so this one, I believe, so on your notes, look right here. I think that you had a different value right here. Okay, yeah, on your notes that I printed, you had a 2. So please change that to a 1/2. The reason I had to change that is because think about what a 2 would do. It would have vertically stretched it. We actually wouldn't have had enough room on our graph for that. So that's why I changed it to a 1/2. Okay, so now I have this function f. Okay, right here, that's a function, vertical line test. Yes, it's a function. I don't have an equation for it, but that's okay. I don't need it. What I'm going to do is I'm going to use the graph to find the graph of this now. So let's think about the two things that's happening. I know there's two transformations because there's a 1/2 and there's a -1. Okay, that 1/2 is on the outside of the function. Outside of the function affects the up and the down, the vertical. Okay, since it's 1/2, think about vertical, it's not opposite. So the 1/2 is a vertical shrink. Okay, what that vertical shrink means, that affects vertical is the y values. So it's going to cut y values in half. Okay, but then right here on the inside, okay, it is subtracting. Okay, adding and subtracting is left and right, but since it's on the inside, it's opposite. So that -1 is actually a shift right 1. So a shift right 1 means that your x values, you have to add 1 to each of the x values. Okay, so now let's take each of these points and do these two things to them. Okay, one thing to the x value and one thing to the y value. So I'm going to do it in red, our new graph here. Okay, so I'm going to start just with this point since it's the for this down point, for this down right. To the x value, I need to add 1. So this point is going to become 5, comma, and to the y value, I have to cut it in half. So instead of -2, it's -1. So that's going to be the new corresponding point. Okay, I vertically cut it in half, and I also shifted it right 1. Okay, so now let's look at the point 2, 2. That point, first to the x value, I add 1, and to the y value, I cut it in half. So 3, 1 is that corresponding point. Okay, this point right here, -2, -2, to the x value, I add 1, and to the y value, I cut it in half. So -1, -1. And then this last point here, to the x value, I add 1, and to the y value, I cut it in half. So -3, -1. Okay, so now when I connect these, okay, notice it's still a function, right? It's still a function, but two things have happened. Every single point was shifted to the right one, and every single point was cut in half, getting closer to the x-axis, that origin. Okay, so again, being able to just recognize what's the transformation, what's it called, what does it make your graph look like, how does it affect your coordinates, x and y, makes it a lot easier there to graph it then. Okay, we only have two last parts of transformations, and that's reflections. Something we've kind of talked about already with symmetry, but what it looks like with full equations. Okay, so now recognize all of our transformations in terms of stretching and shrinking have been positives, either between 0 and 1 or greater than 1. Okay, now we're talking about, well, what if we multiply by a negative? Okay, and that's what's going to cause a reflection. And so think about, again, vertical, up and down. That always happens in the equation outside of the function. So for a vertical reflection, okay, that means it's reflecting across the x-axis from up to down, right? So don't think x-axis is left and right. So this is a flip left to right. It's reflecting across the x-axis. So it is still an up and down change. Okay, while here with the horizontal, we know everything horizontally affects the x. So it is inside the parentheses connected to your x. Okay, that is a reflection across the y-axis. So again, that's a flip left to right. It is a horizontal transformation. Okay, so let's see an example of what each of these transformations look like now. Okay, we've already used our square root here. I'm just going to throw that back on here. 5, 6, 7, 8, 9, 3. Okay, so there's my original function f. Now this negative, because that negative is on the outside, I know it affects the y values. Technically, it is saying to multiply it by -1. And so think about if this is the point 1, 1, the new point on my graph, the x value is not changing. That is a vertical change. It's a y value. So my new point will be 1, -1. 0, 0 doesn't change because when you multiply zeros by anything, it doesn't change. Okay, this new point, instead of being 2, 4, okay, the x value doesn't change. This is a vertical change. So the y value, it will become 2, -4. Recognize, or sorry, I got my original point mixed up here. It's not 2, 4, it's 4, 2. 4, 2. So then that new point is going to become 4, -2. 4, -2 right here. Okay, so recognize it's the same pattern of that parent function, but instead of going up, it's going down because it's a vertical reflection from up to down. Instead of that 0.93, it's going to be 9, -3. So it's going down instead. Okay, and recognize, like, if you were to use your equation, think about what we would do. Like if you plugged in 4, you'd have the absolute value of 4, which is 2, and then you make it negative. So that's why it's 4, -2. Okay, that negative's happening on the outside. Okay, instead, now this one, okay, the negative, look at its location. It is on the inside of the parenthesis. Okay, since it's or inside of the square root, which is technically grouping it inside of the parentheses, that makes it a horizontal change because it's affecting the x directly. Okay, now think about if you tried to plug in positive x values, it'd be like if you try to plug in 1, it'd be the square root of -1. You can't have those. And so think about what has to happen is I would actually have to plug in negative numbers because a negative number would make it positive. And that's why actually now our x values are going to be the negatives. Okay, our graph's going to be going left instead of the parent function who's going right. Okay, so let's think about this as a direct effect of the x values. Okay, so the x values are being multiplied, the y values do not change. So instead of the 0.11 like your parent function has, first of all, I still have 0, 0 because multiplying by 0 doesn't change anything. It's still just 0. Instead of 1, 1, now it's going to be -1, 1. Again, y value isn't changing. The x value is being multiplied by a negative. Okay, picture now, if you plug in -1, it's a negative -1. So it's actually the square root of 1, which is 1. Okay, that's why we need the negatives now. Okay, instead of 4, 2, it's going to be -4, 2. -4, 2. Instead of 9, 3, it's going to be -9, 3. Right? Visually, checking to see, oh yeah, look at that. Okay, my X values were negative. So now I have flipped across the Y axis. Instead of going right, it goes left. And that, of course, does directly affect your domain. So like this domain in the middle, actually these two domains are the same. The domain would be from 0 to infinity because it's going right forever. But the domain on this last one, notice as far left as it goes is negative infinity. So the domain would be negative infinity to 0. Okay, kind of switched around because it's going in a different direction. Okay, so all of those really there's let's count. There's 1, 2, 3, 4 transformations horizontally. 4 for compressing and stretching, okay, if it's vertical or horizontal, so 8. And then 9, 10. There's 10 different types of transformations that you could see on the graph. Okay, a lot of them share some of the commonalities in terms of like, are they inside or outside of your function? And so really there's 3 types. There's shifting, compressing, or stretching, and then flipping. So really 3 different types. So let's just practice writing equations. Like let's say we're starting with this. Let's write a new equation of a graph after this has happened to it. Okay, I'm going to do it in the order stated. So I'm going to start with x squared. The first thing it says to do is reflect about the x-axis. Okay, I need to think about if I flip across the x-axis, that's up and down. Anything that changes up to down occurs on the outside. So that's the first thing I added was a negative. That's the reflection. Now a vertical stretch by 3. Okay, again, vertical is up and down. Okay, so it's still going to be on the outside of my function. Okay, vertical, anything on the outside is not opposite. So that means I still have my negative, but now I need a 3 for my vertical stretch of 3. Okay, now I need to shift right 5. Okay, left and right, that is on the x-axis. So I know it needs to go inside of my x squared. So that means instead of an x squared, I'm going to have parentheses with that shift right being inside of them. And then it's being squared. Okay, so since it's left and right, I know left and right is opposite. Going to the right means I am actually subtracting. So x minus 5 squared. And then the very last thing that I need is a shift down 4. Okay, up and down means it's on the outside. So a minus 4 right here. So let's see, that is our new equation. That's our new function that if you graphed the parent function and then you graphed this is the list of all the transformations that you would see occurred. Okay, last little part here. Suppose the x-intercepts are this and this of some function. Okay, what will the new x-intercepts be after the following transformations? Okay, so you could picture like what this looks like right now. You have x-intercepts here at 1 and here at negative 8. Okay, let's figure out what the x-intercepts would be after each of these transformations. So let's say the first thing we do right here, notice you're adding on the inside, so that's a shift left 4. So that would take every single ordered pair and shift it left 4, which means negative 8 would become negative 12. I don't need parentheses here. Would be negative 12. And then if I take 1 and shift it left 4, it'd be negative 3. So negative 12 and negative 3 would be my new x-intercepts. Okay, here, what this 2 is doing, that 2 is a vertical stretch. What I had started when I was talking about stretching is, remember, stretching doesn't change the location of where you're starting. It changes how quickly your graph is growing. So because of that, you do not change the x-intercepts. They are actually the same. So the x-intercepts would be negative 8 and 1. Still, that didn't change. Okay, on this next one, this is on the inside, so it affects the left and right. Inside is opposite, so it's actually right 3. So that means now negative 8, if I shift it right 3, it's at negative 5. And if I take 1 and shift it right 3, now it's at 4. So negative 5 and 4 would be your new x-intercepts. Okay, our last one, notice the x is negative. So a negative means that there's some sort of reflection, but where is it located? On the outside or on the inside? Outside means some sort of flip up to down. Inside is the flip left to right. So this is we'll call it a horizontal reflection, which means any point on the right side of the graph would flip over to the left, and any point on the left would flip over to the right. And so when we think about -8, that's on the left-hand side. If you flip it across the y-axis, you flip it horizontally, now it's at +8. Okay, if you take 1 and reflect it across that y-axis, now it's at -1. So 8 and -1. It just took every x value and technically multiplied it by -1. Okay, so hopefully with these notes, the examples of the transformations from equations, from graphs, from ordered pairs, all of that is going to come together to help make graphing pretty quickly. Again, I will emphasize, it's going to be very helpful for you to be able to see an equation that looks like this and know what it looks like to begin with. Every step after that will be easier. And so you can always spend time, kind of like we were doing on these ones, to graph the parent function first and see how those transformations visually change your graph, not just from the equation, but on the XY axis as well. Okay, so get into the homework and try that out. Email me with questions, stop by on office hours, and I will see you guys next time.